Now that we've played with polynomials a little bit in their operations, add, subtract, multiply, two types of division, and compositions, we're going to take a look at some graphs of polynomials and inspect their shape and their zeros, their leading coefficients, and all that good stuff. So first off, a polynomial function is always going to be of this form. F of x equals ax to some power n as our first term. And then it's going to continue on with a new coefficient and then x to the, I'm going to put n minus 1. So this just means our exponent is decreasing from what it was originally. And then I could keep going cx to the n minus 2, etc., for however long it needs to go. So you'll notice that there's no fractions in here. Now the coefficients can be fractions, that's fine, but we're not going to have any crazy fractional exponents. They're all going to be whole numbers, positives, no absolute values, no crazy stuff, okay? Now, when we graph a polynomial, there's really only 4 basic shapes, and I'm going to bring up a Desmos graph to show you some possibilities for those Desmos shapes, or for those polynomial shapes. So here I have a function. I'm going to adjust this a little bit. You can see this is the function f of x. That's just ax to the n power. Now, I have my exponent set here as n equals 2. So this is just ax squared. And we all know that's going to be just a parabola. Now, what happens when I jump to an exponent of 4? You can see we still have that parabolic shape. It's a little flatter at the bottom. And again, it is just really kind of flat there. But it's the same general parabolic shape. And when I go to n equals 6, same thing, it's just getting flatter and flatter and flatter. So anytime you have an even exponent, we know that shape is going to be a parabola. Now, if the leading coefficient is positive, like it is here when a equals 1, it's a parabola opening up, just gets narrower as our a gets bigger. If our leading exponent is negative, we know it just reflects over and it gets narrow as that number gets bigger. Okay, so basically even exponent's going to look like a parabola, opening either up or down. Now, when we jump to an odd exponent, I'll turn that guy off and turn on my odd one. This is just an x to the first, which we all hopefully know is just a line. I'm going to increase that to 3. So here's our cubic function. We should recognize that as a cubic function. I know you guys have learned about cubic functions before. Now, what happens when I go to the 5th power? You can still see it looks like a cubic function, but again, it's just kind of flattened out in the middle there. And then 7th, same thing. And then 9th, same thing. Okay, so really, depending on what your exponent is, whether it's odd or even, the specific number itself doesn't matter in terms of the shape. It's really just about whether it's odd or even. And again, if I make my leading coefficient negative, we still have that same shape. It's just flipped over so that the right side is heading down while the left side heads up. And you can see again, even if I increase my exponent, still stays that shape, just kind of flattens out in the middle a little more. Okay, so back to our notes. So here are 4 basic shapes. If we are looking at a function where the biggest coefficient is an even number, we know it is a parabola opening up. Okay. If we have the same thing, still an even exponent but a negative in the front, then our parabola opens down. So even is going to look like a parabola. Now, as for end behavior, really we're just looking to see is what happens on the ends of my graph, on the left side and on the right side. But there's a way I would like you to write it with correct notation. So for this end behavior, I can see that they're both heading up. I would say as x approaches negative infinity, f of x, which is our y, approaches positive infinity. So let's talk about what this means. As x approaches negative infinity, well, negative infinity for x would be the left side of a graph. It's that left side of the number line. So this is really talking about the left side of my graph. What is the y value doing on that left side? It's going up. And as y is going up, it's going to infinity. Okay, so that takes care of the left side. And then I would write a second statement. As x approaches positive infinity, so now we're talking right side for the x value, we can see our arrow is still pointing up. So I would say again, f of x approaches positive infinity. So really this is a fancy way of saying the left side of the function is going up, the right side of the function is going up. All right, let's do the same thing for the negative evened exponent. Still going to start the same way. As x approaches negative infinity, okay, so as x is going to the left, f of x, or our function, is now heading down. So the y value is heading towards negative infinity. That's the down value for y's. And then I would repeat, as x approaches now positive infinity, our y value is still heading down on that right side of the function. So I would keep that at, negative infinity. Okay, so left, negative infinity, right, negative infinity. That's what that end behavior would say. Okay, now let's think about the odd exponented, I'm not sure how you'd say that, those functions. Okay, so if we have an odd function, we said it's going to look like a cubic, where it kind of swoops through, where the right side is heading up and the left side is heading down. Okay, but if we throw a negative in the front, it flips over. So now it's going to be left side heading up, right side heading down. Okay, and again, this is whether it's a cubic or a fifth power or a seventh power or a 21st power, as long as it's an odd exponent. So how about that end behavior? We're going to start out the same way. As x approaches negative infinity, so this would be our left side value of x. You can see the y value heading down. So I would say f of x approaches negative infinity, because it's heading down. And as x approaches positive infinity, that would be our right side, f of x is heading up. So that would also be positive infinity. Okay, so left is down, right is up, is basically what we're saying. And then if we go to the negative one, we would say as x approaches negative infinity, so here's our left side, y is heading up, so f of x is approaching infinity. And on the right side, as x approaches positive infinity, f of x is heading down now, so we would say negative infinity. So that's how I expect you to write your end behavior statements. As x approaches negative infinity, as x approaches positive infinity. And then you're filling in what's happening with the y's. Okay, so those are the general shapes we'll be looking at. All right, only 4 possibilities. Now, specifically, we can find values for our function once we have identified that shape to help us graph. And those are going to be the zeros of our polynomial. The zeros of our polynomial are just the values that are located on the x-axis. So these are our x-intercepts. Okay, so we can say, hey, the shape is this is where it's going to cross the x-axis, and we can draw a nice little sketch. Some other names for the zeros are called the roots. So you may see these referred to the roots of a polynomial function. Or if we're talking about an equation, we can say that they are the solutions of the equation. Okay, so zeros, x-intercepts, roots, and solutions are all referring to those same values. So let's go ahead and practice a couple. We're going to identify the zeros and their multiplicity, and we'll talk about what that means and what that means on a graph, and then we're going to sketch the function. Okay, so first off, the zeros or the x-intercepts or the solutions or the roots, especially if they're factored, are going to come from these factors. So we're going to take our factors, and it's like we're solving the equation. We're setting the factors equal to 0, and then we're going to solve for x. So I can see in this function, if I have a factor of x minus 6, that means we have a 0 at x equals 6. And if I have a factor of x plus 2, then I have a 0 of negative 2. The 3 out front, since it doesn't have a variable with it, isn't contributing a 0. It's just kind of our stretch. That's just going to make our graph skinnier than it normally would be. So think about that as your a value for your function. Okay, so I can see here that we have 2 zeros. If we multiplied this out, this would be an x squared, right? We know an x squared is a parabola, or any even thing looks like a parabola. And with a positive number in front, I know it's a parabola opening up. So specifically, I can say, okay, my parabola opening up needs to cross the x-axis at 6, 3, 4, 5, 6, and it needs to cross at negative 2. What about the y-axis? Because that would be nice to know as we sketch these things. Like, is it a real, shallow parabola? Does it go real low? For a y-intercept, we can always just put 0 in for x. So if you put 0 in for x, this basically turns into 3 times negative 6 times 2, because those x's have gone to 0. So what's that? Negative 36. So it's a pretty deep parabola, and I'm not going to scoot all the way down to negative 36, but I'm going to label it so we can see it. So this parabola probably would look something like that. Okay, again, I knew the shape because it was an x squared. I knew it was opening up because it was positive, and it crossed my x-axis at 6 and negative 2. Okay, how about this next one? This time, let's think about our shape, and then, actually, let's do the zeros first. So I see two factors again. I'm going to set my factors equal to 0. So I've got an x-intercept at negative 1. Second factor, set that equal to 0. I got an x-intercept at 4. This one's a little different though, because it wasn't just x plus 1 as a factor. It was x plus 1 squared. And in doing that, I covered up my square. It was x plus 1 squared. This is what we call multiplicity. Anytime your factor has an exponent on it, that means it's counting for more than one zero. So I'm going to call this a multiplicity of 2. Anytime you have a multiplicity of 2, it's like having a parabola, an x squared, at that value, okay, at that 0. So our function, our polynomial, is actually going to hit the value of negative 1 and bounce right back off. It's going to create a parabola, okay? So we have basically an x squared with another x. That means overall this is an x cubed. It has a positive number in front, so I know it's going to be shaped something like that. Okay, so I'm going to go ahead and do that. At negative 1, I know it touches the x-axis, and at 4, I know it touches the x-axis. And based on what I know about the shape, the right side is heading up, the left side is heading down, okay, because that cubic shape with the right side heading up. Now, here's where we're going to adjust that negative 1. We need to form a parabola at negative 1. I want this graph to hit the x-axis, bounce right back off. So you can see that parabola there. It's still touching it, so it still counts as an x-intercept, but because of the x squared, it's bouncing. I'm wondering how far down the y-axis it goes. What is that y-intercept? So again, let's check it out. If we put 0 in for x, we'd have a half times 1 squared times negative 4. So what's that? Half times 1 is just a half times negative 4, so negative 2. So this guy's actually pretty shallow. So I'm going to erase this a little bit. Let's adjust that. So it comes down to negative 2 before going up to the next one. Okay, but again, having the multiplicity of 2 means it hits the x-axis and bounces right back off before going through the other one.